Now let us look at the questions, past KCSE questions on metals. Now we finished looking at the chief oils, the process of extraction. Now let us go to the questions and check your understanding. The extraction of aluminium from its ore takes place in two stages: purification stage and electrolysis stage. The diagram below shows the setup for electrolysis stage. Name the ore from which aluminium is extracted. We said that you must know every metal and its chief ore. So for aluminium, we said it is bauxite. Bauxite is the chief ore. Name one impurity which is removed from purification stage. The impurities we talked about, we have two impurities which are removed. Number one impurity is iron 3 oxide. Iron 3 oxide, and another impurity is silicon 4 oxide. Sometimes called silica. So these are the two impurities which are removed. You are asked to name one. Label on the diagram each of the following: the anode, the cathode, the region containing the electrolyte. So on the diagram, so it is important you master which one is the cathode, which electrode is the anode, and which one is the electrolyte. Obviously, this is the electrolyte. That is the electrolyte. Then this is the cathode. This is the cathode. This is the cathode, and then finally you can as well label this as the cathode. This wire here is the cathode also, because this is one thing going like this. Then we have the anode. This spring here is for the anode. The anode, these are all of these rods are anodes. So you can name here or even here. And that is the understanding you should have. The melting point of aluminium oxide is 2054, but electrolysis is carried out between 800 and 900 degrees. Why is the electrolysis not carried out at 2054? Why? It's going to be very expensive because it's going to require a lot of energy. A lot of energy will be required to produce that kind of temperature, which is very high. Therefore, the cost of production is going to be high. And if the cost of production is high, then the profit is going to be minimized. Therefore, this one is Roman 2. Roman 2, Roman 1. Why is electrolysis carried out with this? It is expensive. The question is, why is electrolysis not carried? Yeah, it is because it is expensive, because a lot of energy is required to produce this high temperature. A lot of energy is required to produce this high temperature, therefore it is going to be cost ineffective. The profits are going to be lower. What is done lower the temperature? What is done? Remember adding something? Yes. So Roman 2, we add cryolite. By adding cryolite, molten cryolite. You can simply write molten by adding molten cryolite. It is important. These are the things we studied when we were going through the notes in metals. Very nice. Next question. The aluminium which is produced is tapped off as a liquid. What does this suggest about the melting point? About the melting point. If it is tapped as the liquid, then it means the melting point is below 800 degrees Celsius. That's what it means. A typical electrolysis cell uses current of 400 amperes for 40,000 amperes. Calculate the mass in kilograms of aluminium produced in 1 hour. Aluminium is equal to this. 1 Faraday is equal to these coulombs. Very good. So we will calculate the quantity of heat. Quantity of heat first. We will calculate the quantity of heat. You remember, the topic of electrolysis comes before metals because you needed to know how to calculate quantity of heat from the Faraday's law. So quantity of heat is equal to current times time. And this time t must be in seconds. The time must be in seconds. Therefore, our current is 40,000 times time, it is 1 hour. 1 hour is equal to 60 minutes times 60 seconds to change it to seconds. Now, this one will give us 144 million. 144 million. Then, now we have these coulombs. These are coulombs. Another thing you need to remember, it is what the Faraday means. Faraday means 1 electron. 1 ion. So 1 Faraday is equal to 96,500 coulombs, right? But aluminium has got 3 ions. 3 ions means 3 electrons. So we will ask 3 Faradays will contain how many coulombs first for 1 mole. So that is 3 times 96,500 divided by 1, and that one will give us that is 61, 68, 289, 500 coulombs. So 1 mole of aluminium, 1 mole of aluminium ions will contain 27 grams, right? And these 27 grams will contain the total of these coulombs. So I want to say like this. 1 gram, 1 mole of aluminium ions contains 27 grams, and this 1 mole contains 289,500 coulombs. So we will ask the one that we produced, which was produced, that is 144 million, will contain how many grams? So 144 million coulombs will contain how many grams? Therefore, it is 144 million times 27. We are going this way. Divided by 289,500 coulombs. This was coulombs, so coulombs and coulombs will cancel out. So we will have 1343 0.05 grams. Now this is grams. Then the answer was supposed to be given in kilograms. You divide by 1,000. Therefore, the final answer is 13.43 kilograms. Question 2. The diagram below shows extraction of sodium metal using Downs cell. Study it and answer the questions that follow. So this is the diagram. We need to study the diagram. There is a gas coming in here. There's another sodium chloride electrolyte is coming here. molten sodium is coming out here. Then we have the negative, and we have the negative, and we have the positive. This is the positive, that is the anode, and the negative, that is the cathode. That is the cathode. That is the cathode. Then now explain why in this process the sodium chloride is mixed with calcium chloride. What do we say is the function of calcium chloride mixed with the solid rock, sodium chloride? Why is it? The reason was to lower the melting point. So from an A, it was meant to lower the melting point of sodium chloride to 600 degrees Celsius, hence reducing the cost of production. So the reason is why is calcium chloride added to sodium chloride, which is the chief oil? It is to lower the melting point to 600, which is achievable and not expensive, which is cheap. Why is the anode made of graphite and not steel? Why is the anode made of graphite and not steel? Steel would react. Remember, steel is iron. So iron would react with chlorine. Remember, chlorine is produced here. This gas here is chlorine that's going out here. So if they used steel, or steel is made of iron. So that steel will react with this chlorine gas produced and forming iron 3, and that's not what we want. That will corrode the anode. Therefore, it will react with chlorine, while graphite will not. Graphite will not. Graphite will not, but still will react with that. State 2 properties of sodium metal that makes it possible for it to be corrected are shown in the diagram. So you can see sodium molten now, the one which has been extracted, is collected at the top here. And it is floating on the sodium chloride, the molten sodium chloride. Are you seeing that? So which properties do you think makes it possible to be collected in this manner? Number one, the melting point of sodium is lower than that of the electrolyte. Which is sodium chloride. Number two, sodium is less dense than the electrolyte. Another property why it is collected in this way, it is because sodium, molten sodium, is less dense. So it floats on the electrolyte. It is less dense than the electrolyte. Is less dense than the electrolyte. What is the function of the steel gauge cylinder? Steel gauge cylinder, what is the function? So this is the steel gauge, this is the cylinder you're talking about. This is the one. So what is its function? The function is to prevent chlorine and sodium from mixing or from recombining. So this one is meant to prevent recombining of sodium which has been formed, which has been extracted, and chlorine which is going out here. So these are meant to prevent that to avoid any mix-up of the chlorine gas and the sodium, molten sodium extracted. Command 5. Write the ionic equation for the reaction which takes place at the cathode and the anode. Remember, at the cathode is negatively charged, therefore the sodium is going to be extracted there. So at the reaction at the cathode, sodium ions, which is in liquid form, plus 1 electron, is going to produce sodium, which is liquid. What about the anode? Anode is positively charged, therefore chlorine, which is negatively charged, is going to be attracted towards this anode and be discharged there. Therefore, 2 chloride ions in liquid form is going to discharge chlorine gas plus 2 electrons. So these are the equations at the anode and the cathode. Give one industrial use of sodium metal. Give one use of sodium. Sodium is used as a coolant in nuclear reactions or reactors. So there are so many others. You can, at least you should know the uses of 2 uses for each metal. The flow chart below shows the sequence of reactions starting with iron. Study it and answer the questions that follow. So we have iron 3, chloride, step 1, but this step started from iron. So what reagent is required for iron to form iron 3? Chlorine, right? So you just first go through what is happening. Iron is reacting with the dilute hydrochloric acid to form a pale green solution. So iron plus HCl will form iron 2 chloride, right? And that's why it is very green solution. So very green solution, which is iron 2, is added hydrogen peroxide. Hydrogen peroxide is an oxidizing agent. Therefore, we'll oxidize iron 2 to iron 3. And that's why it is forming this one. This is iron 2, will be oxidized to iron 3. Very nice. Now this iron 2 again, it is hydrogen sulfide. When you add hydrogen sulfide, we are going to form a filter, then the solid is going to be iron 2 sulfide. Iron 2 sulfide, right? We are going to form solid phi is going to be iron 2 sulfide. Then yellow solution, adding aqueous solution, sodium hydroxide, then a brown precipitate is formed. Okay, that's a complex. There's no big deal there. So let's go to the question. Name the reagent. Which one have I not mentioned? There is this one. Iron. Oxygen is being added to form a brown solid. Then from this brown solid, solidity heat, step 4. So there is this arrow going up and this one coming. So iron plus oxygen, this is iron 2 oxide. The brown solid, it is iron 2 oxide. Yes. Name the reagent and state the conditions for step 1. This is step 1. So step 1, we need chlorine to react with iron to form iron 2 chloride, iron 3 chloride. Then we need heat. So the condition is heat. Roman 1, we need the reagent is chlorine gas. The condition is heat. You need to heat. Then Roman 2, give the names of the following: solid S, solid V, and solid T. I think we have gone through the diagram together, and we can now get the solid S, solid T. So because I've told you iron plus oxygen to form solid S, that is iron plus oxygen, that's oxidation. So that is, so S is equal to iron 2 oxide. That is iron 2 oxide. Iron 2 oxide. Solid V will be, solid V is, I told you that iron 2 will combine with the sulfide, which is negatively charged, to form the iron 2 sulfide. So solid V is iron 2 sulfide. So here you just need to understand the chemistry of sulfur and its compounds, chlorine and its compounds. That is what is being tested here. Although they are starting from iron as a metal, that's why it is given as metals. Next, solid T. Solid T, where is solid T? Solid T is here. So what's happening? Solid T there. We need, this is iron 2 oxide. What will you do to iron oxide to form iron? That is reduction, reducing. So we need a reducing agent. Which reducing agent we use that is a solid? It is carbon. So solid T is carbon. Carbon is the common reducing agent that is in solid form. Then give reason for the color change in step 2. Color change in step 2. Step 2. So why did the color change from pale green to yellow? Or pale green yellow, or this one here, iron 3 can be brown also at times. It can also be brown. Why did the color change? Hydrogen peroxide. Hydrogen peroxide is an oxidizing agent. Therefore, it oxidized iron 2 to iron 3, which is responsible for the yellow color. Roman 3, I've said that they give the reason for the color change. Hydrogen peroxide is an oxidizing agent. Therefore, it oxidizes iron 2 to iron 3. So iron 3 is the one now is yellow. Therefore, iron 2 hydrogen peroxide oxidizes iron 2 to iron 3, which is responsible for the yellow color. Write an ionic equation for the reaction which takes place in step 3. Step 3, that is from the iron 3 to form the precipitate, which is an hydroxide. This is iron 3 hydroxide. This is iron 3 hydroxide. So because it is the one which forms a precipitate, a brown precipitate. So they want us to write the equation in step 3. That's okay. So step 3, iron 3 plus hydroxide ions, because we are adding aqueous sodium hydroxide. So what is available there we are using is the hydroxide ions. It is going to form iron hydroxide. So hydroxide, you can see from this valence 3, it puts 3 here. So we need now to balance the equation by putting 3 here because of this 3. And that is the equation. This is aqueous, and this is a solid because it is a precipitate. Very important to note. Name one other substance that could be used instead of sodium hydroxide in step 3. In this step, which other reagent could you use? Yes, you can use ammonia solution. Ammonia solution can work there instead. That's Roman 4. Ammonia solution still can work for us. Now, part B. In an experiment 3.36 grams of iron filings were added to excess aqueous copper 2 or sulfate. Calculate the mass of copper that was deposited. Now this is a displacement reaction. Now they are taking us back to electrochemistry, displacement reactions like that. So you need to know that iron, if it is added to copper sulfate, iron being more reactive than copper, it will displace copper from its solution, forming iron sulfate plus copper, right? Yes, so the next thing you can be asked is the observation made. This solution is blue, it will fade, and finally colorless, because this solution is colorless. And then a brown solid is going to be observed. Brown copper is brown. That is observation made. So from this equation we can see the ratio, mole ratio is 1, 1, 1 everywhere. Then we were told that 3.36 of iron was added. Now calculate the mass of copper. So first we need to get the moles of iron. So moles of iron is going to be 3.36 divided by the RFM, and it is given here, RAM is given here 56. That gives us 0.06. So the mole ratio being to 1, 1, 1, 1, so it means the number of moles of iron will be equal to the number of moles of copper, right? So moles of copper is equal to 0.06 because mole ratio is 1 to 1. This one I'm telling you, you don't need to write this one. You just write, when you understand this, that's why we are doing this. We are saying moles of copper is 0.06. Why? We know that the ratio is 1, 1. That's why it was important for you to write this equation. Then next, now we have the moles of copper. What we know, mass is equal to moles times RAM. So mass of copper is equal to moles of copper times RAM of copper, and that is 0.06 times RAM, which is given here, 63.5. And the mass is going to be 3.81 kilograms. The flowchart below illustrates the industrial extraction of lead metal. Study it and answer the questions that follow. Now this is the ore, undergoes roasting in the furnace. There is hot air, then there is sulfur dioxide given out. Then the remaining mixture comes to the smelting furnace where iron is added, coke is added, and calcium oxide is added. Then a gas P is given out. Then a slag is given out, and the lead metal is being collected. So name the ore that is commonly used. Commonly used, they mean the chief ore used in this process. So this is lead metal, therefore the chief ore is galena. Galena is lead sulfide. Galena is lead sulfide, the chief ore for the extraction of lead metal. Explain what takes place in the roasting furnace. What happens in the roasting furnace? In the roasting furnace, some lead sulfide, that is the galena, some of the not all, is converted into lead oxide, and sulfur oxide is given out. In this one, the chief ore is roasted, is burnt. So why is it burnt? So lead sulfide, this is the equation which takes place in the vanace because it is burning to this form. So it's going to form lead oxide plus sulfur 4. Right? So explain briefly what happens, what takes place in the roasting. So some of the lead sulfide tegarena is converted into lead 2 oxide and sulfur 4 oxide. That's what happens in the roasting furnace. Identify gas P. Gas P is carbon 2 oxide, carbon 4 oxide, or carbon 2 or carbon 4. So gas P is CO2, but you are told to identify. To identify, you can use even the chemical or this one. Write the equation for the main reaction that takes place in the smelting furnace. Smelting furnace here. Which is the main reaction that takes place now? Here, the lead that was obtained here, it is the one coming inside here. So here we have lead oxide, lead 2 oxide, which is combining here with the reducing agent. The reducing agent, it depends. If you use carbon, then carbon will react with that to reduce carbon lead 2 oxide into lead plus CO. That's why we said here these two gases will be produced depending on the reducing agent used. So if you use carbon, CO2 is going to be given out and gas P will be CO. That's carbon 2, right? But if you use lead, this lead oxide, and you use CO, carbon 2 oxide as the reducing agent, then carbon 4 oxide is going to be given out, right? Therefore, this reaction will be lead plus CO2, and this is a gas, and this is a gas. So gas P can be either this or this, depending on the type of reagent, reducing agent used. If it is carbon 2, this is the gas. If it is carbon, then this is the gas. So that's why if you give these two answers, this or this, you will get. If you like, the next one is going to be asked, write the equation in the smelting. So either you write this or this, and you will get. So you don't need to write both of them. You just write one of them. Give two environmental hazards likely to be associated with the extraction of lead. Environmental diagram. Okay, I have. What is the purpose of adding iron? What is the purpose of adding that? Why is iron added into the smelting furnace where reduction is taking place? It is added to remove N unreacted, to reduce N unreacted lead to sulfide to lead. So it is added, Roman 4, iron is added to reduce unreacted. So iron is added to reduce the unreacted lead garena, which is red sulfide to lead. That is the function. Give two environmental hazards likely to be associated with the extraction of lead. So we have said, as you can see here, this extraction gives out a sulfur 4 oxide, and we know sulfur 4 oxide causes acid rain, and we know the effects of acid rain to the environment. So it causes acid rain, and acid rain has got numerous effects on the environment. And as you can see, also it causes, it may lead to lead. Lead is very poisonous actually. So lead causes lead poisoning. Lead causes lead poisoning. Yes. Explain why hard water flowing in lead pipes may be safer for drinking than soft water flowing in the same pipes. You know hard water and soft water. Hard water contains magnesium ions and calcium ions. So it means that hard water contains magnesium ions or calcium ions. Therefore, these ions form protective layer of calcium sulfate, right? Or magnesium carbonate, hence does not dissolve lead. Soft water does not form these deposits because they don't contain these ions. Soft water does not contain magnesium ion or calcium ions. State one use of lead other than making of lead pipes. Other uses of lead include use to manufacture lead acid accumulators, that is the batteries, making roofs, radioactive shielding. Those are some of the uses of lead other than making pipes.